Okay, we're recording and continuing with where we left off last time. There's nothing due today or next time for that matter, I think. So you're all kind of examined out anyway, right? Just take a break for a while. All right, so we'll continue this business of carbohydrates, and I hope you had a chance to review a little bit what we did last time, but if you didn't, here's just a jumping off point. So I want to put a word on the title right here. Cyclization, that you know what that means. And we're going to start with a functional group. In this case, it's going to be an aldehyde to a hemiacetal. All right, there's a functional group change that takes place there. There's some stereochemistry. Look out. Got to watch out for it as well. And this will be pulling together several pieces of your background from your organic class. And how about if we start out by, well, I don't know if this is very sophisticated or not, but never mind the chemistry involved for a minute. Just kind of look at what you're doing. What you're going to do is take this thing and imagine turning it on its side. Real sophisticated, right? Yeah, your university biochemistry class turns into turn it on its side. All right, so that's what you're going to do. And from there on out, it's a matter of tracking carbons. There's the carbonyl carbon right there, the aldehyde, and there's number 1. Now notice, I guess this is the hardest part to track right here. Now let's maybe finish these numbers. So 1 through 6, and whatever comes attached to number 1, that had better be number 2. Keep going like that around the ring, keep it little, and don't forget that number 6 is going to stand up like that. Now, why is it like that? You'll see in a minute, but this is going to yield a 6-membered ring. So we'll kind of leave that for the moment. Okay, so what you're doing here in this process is start linear and end cyclic. Although in this case, your ring is not quite closed. Okay, and how can you tell that the ring isn't closed? Well, because there's no bond that holds together a 6-membered ring. This is just getting everything lined up so that you can track what comes next. And so what I want to address next is how to keep your OH groups sorted out from each other. You can see how they're lined up here in this Fisher projection. And what usually is the hard thing to track is, what do I do with those things as I've turned it on its side and I'm just about to draw it as a ring? Well, this right here is on the right, and number 2 becomes down. So there's the map. Look at the carbons, the carbon involved, number 2. Anything on the right is down. The minute I put my finger in there, it has trouble focusing. Okay, then just for the difference, number 3 has an OH group that's on the left, and it becomes up. And that's the trend that takes place all the way. Now, of course, you have, on this side, you have these 2, both on the right, and they become down. Except number 5, I should have said that only about number 4. Because number 5 is different. It has an OH on it that becomes part of the ring. All right, so your general rule, your right OH need to point down. Except for number 5, it becomes part of the ring. All right, that's the main message right there. That's the hard thing to keep track of. And maybe without drawing on this and cluttering it up more, it's heads up here. Carbon number 5 which is this one right here in the straight view, it's got an OH on it, and when you're all done drawing the ring version, there will be no OH on number 5. We'll get to that in this view down here. But the urge is to go, uh-oh, here's number 5, where do I draw my OH group? There is no OH, and I'll make that note in just a minute. So here are the two possibilities right here. This now is what you got when the ring is fully closed. There are two options. And they sure don't look very different unless you know what you're looking for. But when you do know what you're looking for, they're way different from each other. And let's just trace the different pieces of this ring right here. So like I said, carbon number 5, which is that one right there, it's still that one right there. Carbon number 5 contributed its OH, so it would be this one right here. That one is from carbon number 5. You could say the same thing about that. So that's what I mentioned. It's got no OH in it now. And the big difference between these two is where the OH is now on carbon number 1. So that's, before we emphasize the difference, there's one thing about OH groups that totally changes. Carbon 1 now has an OH and no carbonyl. The carbonyl group, which used to be part of number 1, that got bitten in a reaction that closed this ring. That spot right there is where you have the hemiacetal. That's the name of the functional group. So what's the big difference between the two of these? Everything is the same except for just one spot, and it's right here. That OH is up there, and it's down there. That's the whole story. That's the only difference between the two of these. This one right here is called beta, and this one is called alpha. If you want to remember some, I hope, easy method of tracking those names, think that beta means above the ring. It's not real sophisticated, and it depends on drawing it in this orientation, which in this class we always will. The risk of using above is you might think of above and A meaning alpha. Okay, so if none of those methods work for you, don't worry about it, find something. But beta means above. That's the OH, and it applies only to what you see on carbon number 1. The rest of them, all the same. So all OH are the same as before cyclization. The only exception is on carbon 1. Carbon 1 has two options, and they are alpha or beta. Now, what you're looking at in the version of the same two down here is the puckered ring. Does this look familiar from your organic class? Okay, now we're kind of connecting the two worlds. If you were drawing this in your organic class, cyclohexane is all this except for no oxygen in the ring and nothing on the sides. Cyclohexane itself, not all that interesting biologically, but all you have to do is envision, oh, I've got an OH on each one of the carbons to make the whole thing water soluble, and instead of one carbon in the ring, I've got an oxygen. Otherwise, everything's the same, and you can talk about positions on the rings. So this one being up is beta. This one being down, that one's alpha. And then let's kind of look at some of the others and make a little comparison. So I'm going to move to carbon number 2. In that version up there, it looks like carbon number 2 has an OH on it, and the OH points down. And that is indeed what you've got right here. So that one's down. This one, number 2, had better be the same, which it is. So there's number 2 and number 1. And I'll do one more, just to make sure it's consistent. It looks like on carbon number 3, in this flat view of the ring, you have an OH that pointed straight up. And sure enough, your OH here points up, just like it does on the flat version. This is where it gets to be kind of important to remember your old terms, axial and equatorial. Does that sound familiar at all? Okay, now look what nature has handed us here. This is glucose. And do you remember from your organic class which positions are easier for things to sit in? Do you want as many axial or as many equatorial as you can get? Anybody remember? Well, equator means kind of like the equator of the world, right around the middle. Whereas axial means, and I'll dot them in here, straight up or straight down. That's where the OH would be sitting. All of these are carefully avoiding being straight up or straight down, as nature has handed it to us, and there's a reason for that. You get too many of them in axial positions, they start bumping into each other. The equatorial ones are the most stable spots to be, and wouldn't you know, the most stable sugars, monosaccharides, have their OHs all in equatorial positions. Around the middle of the molecule, they're as far away from each other as they can get, so there's no steric crowding around the top of the ring. No wonder this is the way nature hands glucose to us like this. Now there are others where, yes indeed, one of these is different. So the molecule accepts some crowding, and maybe it has a biological role that justifies all that. But if you want to think the parent monosaccharide compound, think glucose, and every last one of those OHs is splayed out as far from the others as it can get. No wonder that molecule is so stable and so common. Everybody's happy. Nobody is crowding each other around the middle of the molecule anyway. Okay, see, your organic did actually turn out to be useful for biochem somehow. You may be struggling to think about it. Okay, so, well, before moving on from that page, let me see if there are any questions on that. Now, we'll do something similar on the next page, but in a little less detail and maybe a little less time involved. Now, look at the big difference here. This one is cyclization to a 6-membered ring, and sure enough, we've got your familiar hexagon and the puckered ring looking like that. But it doesn't have to always be that way. There are 5-membered rings out there. You eat one of them every day if you're eating table sugar. And so let's talk about what it looks like when that happens. 5-membered rings are not as stable as 6-membered, but they are stable enough that they matter, and they're definitely there. Well, in this story right here, don't be afraid, just number. So 3, 4, 5, and 6. Now you're looking at only 3 spots where you have a carbon that has an OH on it, and the carbon is a stereocenter. And then if you do the same wraparound over here, it looks like this. 3, 4, 5, and 6. Okay, again, this is a chance to stress what you're doing here. You're going to turn on the side of the compound. And also, this wouldn't be a waste of time at all. Remember, this is on the right. That means this thing is a D sugar. The last stereocenter in the line is always going to be a D. So you can kind of assume it'll always be on the right. All right, so once again, the story is that this version that you've bent right here can now form, there are 2 options, 2 possible rings. And I guess the challenge right here is to notice the difference in ring size. The bond now, the new bond, is going to destroy the carbonyl group on number 2 instead of number 1, which we did in the first example. And would it be possible for this to form a 6-membered ring? Yes, it would. You would need to use carbon number 6 to bite number 2. And there are cases where that happens. But what I'm doing right now is illustrating how to get yourself to essentially fructose in its cyclic form. All right, let's keep tracking everything right there. There's number 2 and number 2 in those 2 spots. And notice the difference between these two. This OH right here is down, and here it's up. And of course the other partner, the CH2OH, has to take the other position. But that's the only difference right there. So again, you're looking at, I'm going to use number 3 as an example, to number 3. Here's up. This is up, and number 3 in the straight form was on the left. That's why it points up in the cyclic version. Okay, and the big difference right here, I think you can see this, but let's add this. Carbon 2 in this version was the one that reacted. Carbon 2 now has an OH. What it used to have was a carbonyl. The carbonyl is history. But like I said, less detail on this one. Again, you got 2 optional products, but the reaction itself is the same. 5-membered ring instead of 6. Happens all the time. Okay, and I don't think it's worth the added detail of the puckered ring down here or anything like that. That doesn't really add any new concepts or anything. So those are the 2 different routes that get you to 2 different ring sizes, 6 or 5. Those are the bread and butter structures of monosaccharides. If you got those, you've got all you need to know for this level of class anyway. So let's put some terms on these. The 6 and the 5. Both of them have their own terminology. And now notice, if you're going to use these terms right here, you're putting yourself in a box, which is true most of the time. These terms must refer to a cyclic sugar or monosaccharide. And there's a term that gets applied to them. The first one is a pyranose. It's named for a compound that you don't need to know by name, but I'm hoping that it will help you tie to the sugar name itself. This compound right here, I hope you'll recognize as that's the ring that you'll find in all 6-membered sugars. Okay, it's cyclohexane except with an oxygen dropped in. This thing right here is called pyran or paran, and so the name of the sugar made from that basic core you call a pyranose. And then the other term, which applies to the 5-membered ring, is from this parent compound, and that's from furan. You don't need to know those words, but you do need to know these. These right here, certainly don't memorize those. If you do happen to know them from your organic class, fine. If you don't, that's okay. Then there's a term about the so-called anomeric carbon. So what's that? Well, it's the carbon where the carbonyl carbon used to be. It was the carbonyl carbon. It's now going to be in the ring something that you'll label either C1 or C2, depending on if you're talking about a 6-membered ring or 5-membered. That's just talking about that one carbon, that one spot that reacted. And then the anomer term is these compounds that differ only in the configuration at the anomeric carbon. In other words, alpha or beta forms, you would say that they are anomers of each other. You'll hear the term the alpha anomer or the beta anomer, and it just means a precise term They differ only at one carbon. So you can string together now, using these methods of naming and these terms, you can string together this whole set of words that matter for ring, not 60, that's size, ring size. Okay, your anomer name is going to be either alpha or beta, and the relative configuration is going to be D or L. The natural ones are exclusively D. The name of the linear form. Now, you've got a whole bunch of possibilities here. Let's say you're going to have this as unique. There's one for each linear form. So it'd be things like glucose, lactose. Both of those are six-membered. And you could also talk about fructose. All of those are 6-carbon monosaccharides. And then the ring size would be the last thing you'd be talking about with a word. And there's only a couple of options there. One of them is pyranose. The other one's furanose. Okay, so let's pull together an example or two. An example, I use this. I'm going to start it here, beta, and then D for the natural one, fructo, furanose. Okay, so that's telling us a story. It means this. Starting with the word, what you would know is you're looking at fructose now folded into a 5-member ring, which is its favorite. You'd know something else. So from the name, that is, it means that this has an OH on the anomeric carbon that's pointed up. And the last thing you would know is, still on screen, yeah, it's in the natural D configuration. All of those are packed into that one word. So you tell a lot about structure just from the name itself. Well, any questions from that? Have you seen any of this before? Hope you've seen rings anyway from your organic experience. Okay, so we'll move to just a couple of other brief things here that do fall into the same bucket. They're all monosaccharides. And the story here is that you don't have to stop with these as molecules that you metabolize. So derivatives are compounds that are made usually by adding something to a monosaccharide. Okay, so what would it look like? Here's your parent compound, let's say, and a little chance to review as well. Okay, so we've got a name here, and let's just review that part real quick. Beta means that the OH on carbon 1 is up. Then there's D. D is natural, and D refers to the last chiral carbon, which is number 5. And then the pyranose. Okay, let's think what that means by way of review. Pyranose means a ring with 5 carbons and 1 oxygen atom. Okay, so there's the 2 facts that I guess I'd pull out. So there's your parent compound. That is glucose bent into a ring. Now, there's other stuff that you can put on this. Here is a derivative. So let's make sure that we're labeling the parts of the world that we're moving into. This is one derivative. And you're technically at liberty to replace any OH group or any hydrogen with anything else you want. Nature uses this just like a synthetic organic chemist would. It's like, okay, what can I put here? So one of the simplest things you could put is an amine group right there. Now that's that would be on carbon number 2, right? So there's 1 and 2. All right, if you make a compound that starts with glucose and you put an amine on it, what do you suppose you'd call the whole thing? This is used as a nutritional supplement. You heard of glucosamine? Ever heard of that? To tell you the truth, I don't know what do we call it? Folklore, folk medicine, things like that. I don't know what they think glucosamine does. Maybe some people really do benefit from it. But there's one example of a derivative, glucosamine, for obvious reasons. It's not just a simple monosaccharide anymore. It's something that started life with a parent monosaccharide and was transformed into something else. And then there's another version that says, well, okay, why stop with that? We know how to make derivatives of amines. You would have had a chapter on that as part of your organic class. Let's say that we are not content with the amine. We want to make an amide out of it. That's another derivative. And this one has a name, N-acetyl glucose amine. And that one is not just a folk remedy. That's an actual constituent that your body uses to make cartilage. That's an honest-to-goodness biomolecule. And it's a way of, what do you bet? It's a way of making the whole tissue biocompatible. It's going to polymerize the glucose units by a route that we'll see later. Here's an amide that really will deaden the reactivity of this whole part of the ring right here. Probably a way of starting with a carbohydrate background and making it really, really stable, which you want of cartilage, right? If you tried to make connective tissue out of a glucose polymer, the minute you got hungry, you'd start losing tissue and breaking joints. Okay, not a good strategy, right? So there was a reason for nature to derivatize this, but still be able to make a common polymer and use it for something much more tough and structural. Okay, not a bad strategy. Okay, then there's another way to think, another type of derivative. Instead of having an amide or something like that, like you see for glucosamine, you're looking at a functional group that's an ether. Okay, now you're going to get your functional group here from one spot in your monosaccharide molecule. This is going to be something, the oxygen source for the ether will be something that starts out in the monosaccharide. And I'll go ahead and say carbohydrate to make it a little bit more general, because it doesn't have to be just monosaccharides. They can be bigger molecules too. So your functional group, which is an ether, I hope you remember, 2 organic groups bridged by an oxygen in the middle. And so we'll say that this much right here is from your carbohydrate, and this much right here is from something else. Now the catch here is, remember, the something else could even be another monosaccharide. That's the way monosaccharides get bigger. So could even be another monosaccharide. All right. And like the statement says, they're ethers made by etherifying one or more of the OH groups. Now, here's the simplest, probably the simplest version of it that you could imagine. Imagine that your molecule that's going to tack on to make the ether is just a little bitty alcohol. So that would be saying that we're going to focus on this carbon. It wouldn't have to be this one. Choose carbon number 1, its OH group, and now, as of right here, this is an O glycoside. It's an honest-to-goodness ether. Which is actually part of an acetal, if you're trying to be precise about it. That carbon right there is now an acetal carbon. Okay, but the point is you've got something new on the oxygen. Okay? Any one of these oxygens right here is fair game for derivatizing, and I'm not sure if we get to this on the unit on starch or not, but you may know that one way to make foods thicker, I say foods in general, liquids thicker, like a salad dressing or anything like that, a liquid that you want to thicken. If you look on the list of ingredients, it'll say something like derivatized starch or derivatized carbohydrates or something like that. Well, all you're doing here is, with that kind of ingredient, is start with a slightly bigger molecule instead of just the monomer right here. And there's a reason that the thickening agents are made by corn millers. Corn is a good source of starch, and if you know how to do chemistry on cornstarch, you can turn it into something that's worth a lot more money than just cornstarch, like these thickeners. Okay, they do, and I hope I never do this in my career, they do the reaction of cornstarch plus acetic anhydride. Okay, acetic anhydride is this extremely reactive compound, and it will go and chew onto the OH groups right here and come up with a polymer that's suddenly a lot more, big and wobbly and so forth like that. So you can take a basically cheap, thin salad dressing and throw in one of these thickeners for pennies and end up with something the consumer thinks is, this is really good concentrated stuff. It's this thick. You have to kind of shake it to pour it and this kind of stuff. It must be really loaded with the ranch flavoring, which is what I'm paying for. Well, no, not really. That was some tricky biochemist and organic chemist monkeying with a biomolecule, doing not this reaction exactly, but something a lot like it. You just monkey with the OH groups on a carbohydrate, and you change the physical properties, the metabolic properties, is what I'm trying to say. You can monkey with all kinds of properties just with a few reactions, because there's so many of these things, these OH groups, to serve as targets in your biomolecule. Okay, that was a little bit of a distraction, I guess. Okay, so there's a natural bridge from there to disaccharides, which is what we'll end with for the day. And this is now the first step toward getting to much, much bigger molecules. And so if you're talking about a disaccharide, here's the simplest way to think about it. So here's the, this is going to be the beta form, because the O is pointing up, and here's alpha. So those are your two options, working with just that one carbon. And if what you're envisioning here is something that's another monosaccharide, you are now looking at a disaccharide. Keep this pretty general at this point, maybe. Another monosaccharide. And same here. That's all we're talking about. And so we're starting out with the assumption that the linkage is happening on carbon number 1. And that's exactly where it is for most of them. There are enough of these, and they are important enough that there's a set of terms that has come up just around this version, things linked at carbon number 1. So you start by numbering them, and you need to make sure that you talk about alpha or beta for carbon number 1. That's part of what goes into the numbering. And that's where you start. And then you're going to have a carbon number on your first ring, and you're going to have an arrow. The other thing that you'll be specifying, so you know what you're looking at, is your carbon number on the second ring. Alpha or beta applies if you're talking about carbon number 1. So here's what I'd like you to be able to do for this class. If you're given a structure, be able to call it alpha or beta. That's pretty standard so far. And if you're given a monosaccharide structure, or more than one, be able to put together a disaccharide. And here's the way that would work. Okay, you don't want to go memorizing the structure of glucose at this point. But let's talk about how the names and the structures would work together. All right, remember, put another little review note on this page. Alpha or beta, that refers to the so-called anomeric carbon, and that is your old carbonyl carbon. It's not a carbonyl anymore. All right, so here's a compound. This is a disaccharide. It's called cellobiose. Here's another one. This one's also a disaccharide. This is another one. What both of them have in common is they're two monosaccharides together, and now it's heads up because you got to specify what the two monosaccharides are and how they're connected together. So let's come up with some language right here. All right, carbon 4. Here's 1, 2, 3, and 4. Let me do that for both rings. 1, 2, 3, and 4. This carbon 4, this one right here, is not alpha or beta because it's not on carbon number 1. It's not part of the anomeric carbon. That's just carbon number 4. And in glucose, it will always point down. You don't have to remember that. You just have to be able to connect from a structure that you're given. So this one always down in glucose. There would be natural sugars out there that pointed up, but we're good for now. And so then you look at number 4, and sure enough it's down there, but that's not part of what holds the two rings together. There's carbon number 4, its OH is down. So far so good with that. Now what you can tell about this carbon though is, yeah, this one is part of the anomeric carbon. That one is part of the list. The anomeric carbon is, in this case, beta. That's because it's above the ring. And so you're now going to draw a map from this thing to this one. Here's your first, and here's your second ring. Okay, so let's put all this together in the kind of linkage. All right, the first thing you say about it is you start with the first ring, beta. First ring, and it's carbon number 1. You can then move on to it, onto the rest of the name, and say, well, the carbon number on the first ring is number 1, and the carbon number on the second ring, the other point of attachment, is number 4. There's your first ring again. Here's the second one. Okay, you're thinking, oh man, that is so picky. But think of the difference here. All you would have to have is a difference between carbon number 1 pointing down versus pointing up, and you would have a different biological molecule, different stereochemistry. I read an article several years ago about just disaccharides, and it turns out to be important in nutrition of infants. And by that I mean just a few weeks old. And think of what the options are here. You have, in this, just take one ring at a time, you've got 1, 2, 3, 4 stereocenters. So that means you'd have 2 to the 4th stereoisomers naturally occurring. We're looking at just one of them here. So that would be 16 rings, 16 natural rings here. They would have different names. One would be glucose, then you'd have galactose and other stuff. And then if you take those 16 possibilities and start linking them up with just one other ring, which also has 16 possible versions of it, the number of possible products just blows up immediately. And wouldn't you know, it turns out that there's a difference in infants who feed on their mother's milk, those that are breastfed to begin with, and those that drink formula. Now that's not to say that it's fatal to use formula or anything like that, but the thinking is that this rich mixture, really diverse mixture of compounds, just disaccharides, feeds a select set of bacteria in the gut of a newborn that allows them to start metabolizing better to begin with. Now, I don't know if that's totally nailed down with, but if you want to discount the importance of just 2 little rings tacked together, look to infant nutrition. Okay, it's probably much more complicated than we even understand at this point. Just one stereochemically different point. Okay, so let's finish this up, this last ring. So again, we're looking at carbon number, and in this case this is number 1, but heads up, this is number 2 on the bottom ring, because you're looking at a 5-membered ring. This one is beta because it points up, and this one is alpha because it points down. So look out, again, you're referring to the first ring, which is now connected to a second ring which is pointing up. I could have drawn them backwards. I don't know if that would have made it easier to see or not, but this keeps the rings oriented the same way. So let's do our kind of linkage. And again, look out. I won't do all the numbers, but it's awfully tempting to look at the carbon in the corner, the one next to the oxygen, and say, oh, there's number 1. Not quite. Okay, look out here. It's actually number 2, and there's number 1. That'll matter for the name, and it matters for the structure. Kind of linkage. We'll put a name on this. Okay, now this time we've got to specify 2 different words because the linkage is to the anomeric carbon on both of the rings. So you start with your first one, and you go alpha. Okay, so that one right there is from your first ring. And then next you look at the second ring and you go beta. Okay, and that is on your second ring. And then you're going to have a number pointing at another number. And I'm hoping by now you're starting to get the hang of it enough to give me both of those numbers. So start with the first one, which is that ring right there, the one that's drawn up on top. What number do I put in the left-hand side of the arrow. That's number 1. And how about the other one? 2. Yeah, sure enough. Now, the comparison you want to make here is you've connected, starting with the same parent compound, the same first ring, you can do very different things with it, like going 1-4 or 1-2, depending on where you connect in the other ring. It would have been possible to make a 1-4 linkage in this whole thing down here by connecting to that carbon right there. I'm not going to try to draw that possibility. You draw rings all day long, right? Just to get the possibilities that nature could throw at, and apparently does throw at us in human milk. It turns out to be important for nutrition of the baby. I think that brings us to the end of where we had to be today. Am I right about that? Looking to the syllabus, let me just make sure that we're on schedule. And yes, we are. Okay, so let's call it good for Friday, and hope you have a good weekend and relax and don't think about biochem too much, but don't forget it totally, okay?